Hi physics, so welcome back. This is going to be part 2 of this video. So we're in homework 3, problem 5. We're trying to figure out a lot of different things about this particular circuit. So we've already done the step, those are all of the things. We took the circuit, we simplified it, found our equivalent resistances, simplified it again, found one equivalent resistance, figured out the current used by the whole thing, figured out the power used by the whole thing. Then after that, I went back to my middle kind of simplified thing where I had two equivalent resistances. And I used the current I'd figured out to figure out the voltage drop across each equivalent resistance. So now we get to kind of a key idea. If I look up here and I see this, the voltage drop across the first equivalent resistance, V equals 6.428 volts. Well, I actually know that that is the voltage drop across this guy and the voltage drop across this guy. 6.428 volts. And the other idea I have here, the voltage drop across the second equivalent resistance, 11.571 volts. So that is the voltage drop across V3. 11, I'll make that nicer, 11.571 volts, and that is also the voltage drop across V4. So V4 is 11.571 volts. So that's a lot of the other things I want to figure out. So remember, what am I trying to figure out? The voltage drop across each resistor, also the current through each resistor, and the power used by each resistor. So we're going to take those ideas. We'll start with R1. So for R1, let's see. So V1 is equal to 6.428 volts. Okay. That was actually my answer, one of my answers for part D. I'm also trying to figure out the current through this. Okay, well, current, V equals IR. That means I is equal to V over R. So I1 is going to be V1 over R1. So 6.428 volts divided by resistance. The first resistor is 25 ohms. And let me check my sheet. That's going to give me a voltage of, a current of 0.2571. 2571 amps. So that's one of my answers for part E. And finally, the power. The power from 1 is going to be, use Watt's law, I1 times V1. So 0.2571 amps times V1, 6.428 volts. This is going to give me a power of 1.653 watts. And that's one of my answers for F. So if we got one of these guys done, let's go on to the next guy, figure out what those are. So for R2, V2 is equal to, it's the same voltage, 6.428 volts. So that's one of my answers for D. To get the current, we're just using a version of Ohm's law. I2 is going to be V2 over R2. 6.428 volts. R2 is 50 ohms. So plug that in the calculator, and you should get 0.8266. Nope, sorry, looking at the wrong number. 0.1286 amps. So that's one of my answers for E. And then P2, and again we're using Watt's law. P2 is going to be I2 times V2. Let's see. I2, we just figured out 0.1286 amps. V2, 6.428 volts. So the power across this guy ends up being 0.8266 watts, which is one of my answers for F. And we just keep going on like this for the other guys too. But I'm actually going to do it because I want to see. I want a new color. I need more colors. I'll go with black. Squeeze it in down here. For R3, we know that the voltage across R3, so V3, 11.571 volts. And that is part of our answer for D. I3 is going to be V3 over R3. So 11.571 volts over R3's 50 ohms. That's going to give us 0.2314 amps. This is an answer for E. And then finally P3 will be I3 times V3. So 0.2314 amps times V3, 11.5, clean that up. Sorry, struggling with this pen. 571 volts. P3 ends up being 2.678 volts. I'm sorry, 678 watts. There's one of my answers for F. And finally, what haven't I used? I'll go back to blue. For R4, V4, 11.571 volts. I4 is going to be V4. It works over R4. 11.571 volts over R4 is 75 ohms. So I4 is going to be equal to 0.1543 amps. And finally, P4 is going to be I4 times V4. So 0.1543 amps. I gotta clean that up. 0.1543 amps times V4 is 11.571 volts. Do those together, and the power here ends up being 1.785 watts. So that's an answer for F. This was an answer for E. So I've done all my things, but I want to actually point out a couple of interesting things that are going on here. First of all, let's go back to the other picture. And we notice that the current leaving the battery was, I don't want to drag it around, it was this number here. Sorry, I don't know how to use the pointer. It was this number here. 0.357 amps. Okay, now let's go back and look at this. So you've got that I already forgot the number. 0.3857 amps. So that is the current that's leaving here. So that's the full current leaving the battery. Actually, I should be doing it here. So notice at this juncture here, so that's I, that's going to split into I1 going this way, and I2 going this way. So what that means is I1, if I is going to become I1 and I2, then I1 plus I2 has to equal I1. So I1, that was this number here, 0.2571. I2, this number here, 0.1286. If you add those guys together, you do get that original current, 0.3857. And the same thing is going to happen. So these guys go around. I2 comes back up here. And now these guys join together again. So these guys are now equal to I again. So these were equal to 0.3857. And then what happens is it splits here into I3 and I4. So again, we know that I3 plus I4 has to equal that original number, whose units are neglected. How unlike me. So yeah, if you take your number for I3, 0.2314, add it to your number for I4, 0.1543, add those together, and you do in fact get 0.3857 amps. So that comes together. Sorry, these guys come together. And they become I again, down there at the bottom. So that's how, that is Kirchhoff's current law, how that works. The other thing to notice is, if we go back, we figured out the total power of this whole circuit, of everything all at once, is 6.943 watts. Well, what do you think is going to happen if we add up all of the powers used by the individual ones? If we take 1.653 watts, add it to 0.8266 watts, add that to 2.678 watts, and add that to 1.785 watts, we're going to get that original power, 6.943 watts. There's probably some rounding in there that makes it not exactly right. But yeah, the total amount of power that the battery is providing has to be the total amount of power being dissipated by all of the resistors, because of the law of conservation of energy. So there's a lot going on here. Yeah, if you just look, it's a lot of small math. It's a lot of drawing and redrawing. It's a complicated story. All of the little steps are fairly easy on their own, but there's so many little steps. So hopefully this was helpful. Yeah, just do enough of these problems that you figure out your own style that is clear and you can follow what your work was. Hopefully that is helpful.